We are jumping into one of the most exciting recent papers in controllable video generation.
Well, this one is a huge deal.
It's called Wan-Move, Motion-controllable video generation via latent trajectory guidance.
Right, and it really tackles this core problem of precision control, but in a way that's surprisingly simple and scalable.
Absolutely. So for a quick 60-second summary, let's break down the 3 key takeaways you need to know. First, the big innovation. Latent trajectory guidance. They found a way to control motion just by directly editing the model's latent features, which means they get to completely bypass things like control nets.
No bulky, complex modules. It's basically architecture-free control.
Exactly.
Yeah.
Key insight number 2. This efficiency leads to, well, amazing results.
Yeah, the quality is just top tier. We're talking 5-second 480p videos where the motion control is so fine-grained that it actually rivals commercial tools.
They specifically mention Kling 1.5 Pro's motion brush in their human evaluations.
Which is incredible, getting commercial-grade control from an open research paper.
And finally, key insight 3. And this is a massive contribution to the whole community.
MoveBench.
They released MoveBench. It's this large, meticulously curated benchmark, over 1,000 videos, all 5 seconds long, with these rigorous human plus SAM annotations.
So if you want to properly evaluate motion control from now on, MoveBench is pretty much the new gold standard.
It really is.
I mean, it's just such an elegant solution. Previous methods, they always had this trade-off, right?
Always.
How do you inject these very specific motion signals without either, wrecking the visual quality or forcing you to bloat the model with extra components?
Components that slow everything down, training, inference, all of it.
And Wan-Move just sidesteps that entire dilemma.
Okay, so let's unpack that core mechanism. How does it actually work? In the past, you sort of had 2 kinds of motion control. Sparse controls, like a bounding box.
Right, which gives you a general idea of movement,
Yeah.
but it's not precise, no fine detail.
Or you had the other extreme, dense signals like point tracks.
Where you're literally tracking thousands of points over time. That gives you precision. But integrating that into a model has always been the painful part.
Right, because you'd usually need something like a control net. And for our listeners, a control net is basically a whole duplicate network.
A copy of the main architecture, yeah. And its only job is to learn how to translate a condition, like motion tracks, into the right kind of guidance for the main model.
It works, but you're adding millions of parameters. It makes everything more complicated.
So Wan-Move just asked a different question. They said, hold on, what's the fundamental job of an image-to-video model?
To animate the first frame.
Exactly. To animate the first frame, which is conditioned on its latent representation, we'll call it Z image, Dan. Their whole idea is built on something called translation equivariance in the VAE latent space.
Translation equivariance? That's a bit of a mouthful. How should we think about that?
Just think of the VAE features as these super compressed semantic maps of the image. If you move an object in the real image, its representation in that latent map also shifts in a predictable way.
Yeah.
The spatial relationships are preserved.
So the latent features know what the object is and also where it is.
Precisely.
Yes. Why not just move the features themselves along the path we want?
That is the core idea of latent trajectory guidance. They start with dense point tracks in pixel space, the motion you want. And they just map those points into the latent coordinates. It's a simple translation, no complex encoding needed.
And this is where the real magic happens, right? Latent feature replication, or LFR?
Yes. So for every single point track, they go to the first frame's latent condition, Z image, and they grab the feature vector at the starting point.
Okay.
Then they take that exact feature vector and just copy it, replicate it along the entire path of the trajectory in all the future frames.
So they're taking a little high-fidelity sticker of what the object looks like in latent space and just pasting it where it needs to be frame after frame. But wait a second. If you're copying a feature from frame 1 and pasting it into frame 50, what happens if the lighting changes? Like if the object moves from sun into shadow?
That is the critical subtlety here. They're copying latent features, not raw pixels.
Yeah.
And those latent features already contain so much rich local context. Texture, what the object is, surrounding details, it's all compressed in there.
I see.
So when you replicate that, you're preserving the object's identity like, this is a hand holding a red apple. And the diffusion model is smart enough to handle the rest to fill in the changing background and lighting.
So LFR is non-parametric, no new weights to train. It's just a clever trick with the input signal. And because it's copying rich features, the motion looks more natural.
It is a fundamentally more scalable way to do this. And their ablation studies really prove why this works so much better than the alternatives.
Let's get into that. They tested it against a couple of other ways you might think to do this. First up was pixel replication.
Yeah, and pixel replication, as you probably guess, was terrible.
I can imagine.
They just copied the raw pixel color along the path. The result was a really high endpoint error, or EPE, of 3.7.
Okay, let's define that term. When we say EPE, endpoint error, what is that measuring?
EPE is all about accuracy. It's the average distance in pixels between where the control track said a point should end up and where the model actually put it.
So lower EPE means more precise control.
Exactly. And an EPE of 3.7 means it's missing the target by almost 4 pixels. The control is just really weak.
Which makes total sense. A single pixel is just color. There's no semantic context for the model to work with.
None at all. So the second alternative they tried was a bit closer. Random track embedding.
Okay, so they still use the trajectory path, but instead of the rich latent features, they used a learned random embedding to guide the motion.
And it was better, but still not great. Lower PSNR and SSIM. And it created what they called stiff motion.
Stiff motion?
Yeah, the example they give is perfect. Imagine you want to move a hand holding a piece of bread.
Okay.
With this random embedding, the hand might follow the path correctly, but the bread just stays frozen in place.
Because the simple embedding didn't carry that crucial context, that the hand and bread are one connected object.
It lacked that local semantic richness. But with LFR, which uses the context-rich latent features, boom, lowest EPE at 2.6, highest PSNR, it's definitive proof that their approach is the right one.
It just connects all the dots. You get efficiency and you get quality at the same time.
And now we get to scalability, which is the part that I think any ML engineer listening needs to hear, the condition fusion strategy.
Right, the comparison with ControlNet. It's honestly staggering when you think about deployment.
So a standard ControlNet baseline using the same model backbone got pretty similar results, an FID of 12.4, an EPE of 2.5.
Okay, so quality-wise, it's in the same ballpark.
But the time cost. ControlNet added 225 seconds to the inference latency.
Wait, 225 seconds? That's almost 4 minutes of extra processing time just for the motion guidance.
Per video.
For any real-world application where you need speed, that's a complete non-starter.
Absolutely. Now contrast that with Wan-Move, their LFR method, followed by just a simple concatenation with the input noise.
It got a better FID, 12.2, and a comparable EPE of 2.6.
And the inference time cost.
Let me guess, it's a lot less.
It added about 3 seconds.
3 seconds.
Mostly for the one-time trajectory extraction. So you're trading 4 minutes of overhead for 3 seconds while keeping or even improving the quality.
That's not an incremental improvement. For anyone building a production system, that's a game changer.
It really is. And they did this by fine-tuning a massive model, the Wan i2v14b backbone, on 2 million high-quality videos. The data curation was also super rigorous.
Yeah, I saw they used manual scoring and a siglip check for temporal consistency.
Right, that siglip check is important. It's basically comparing adjacent frames to make sure they're semantically similar. It filters out glitchy or incoherent videos from the training set.
It just shows the level of detail they went into. I also liked the training strategy, how they kept a 5% chance of dropping the motion conditions.
That's such a clever regularization trick, isn't it?
It really is.
By sometimes forcing the model to generate a video with just the text in the first frame, you make sure it doesn't forget how to be a good general-purpose I2V model.
It maintains that baseline quality, even when the user doesn't provide any motion control.
Exactly.
Okay, let's shift gears to the other huge contribution here, MoveBench. Why did we even need a new benchmark for this?
Well, the existing ones like Davis or MagicBench just weren't cutting it anymore.
Why not?
Davis clips are really short. And MagicBench, while bigger, use noisy, automatically generated labels, so you couldn't always trust the ground truth.
And MoveBench was designed to fix all of that.
Right. It was built from the ground up to evaluate long, complex motion. We're talking 1,018 videos, all 5 seconds long, 81 frames.
And the annotation quality is key.
It is. They used a hybrid pipeline, a human working with Sam, to get these super precise point trajectories and masks, even for multiple objects at once.
Plus, they used models like Gemini for the captions to make sure they were detailed and focused on motion.
And having that high-quality benchmark is what makes their results so convincing. Wan-Move just consistently outperformed all the other big academic models.
Yeah, it achieved the lowest for Chev video distance, FVD, of 83.5, and the lowest EPE of 2.6.
And let's quickly clarify FVD for the audience. We said EPE is accuracy. FED is more about visual quality and realism.
Right. It measures how similar the generated videos are to real videos.
A lower FED score means your videos are smoother, more realistic, more temporally coherent. They just look better. And hitting the lowest FED proves their method doesn't sacrifice visual quality for control.
That holds up even in the really hard cases, right? Like multi-object control.
Oh, especially there. That subset of MoveBench has almost 200 videos with multiple things moving independently.
Which is usually where models start to fall apart. Objects merge or you get weird artifacts.
But Wan-Move was significantly better than the baselines there, a much lower FED and EPE. It just reinforces that the context-rich features help the model keep track of everything.
And they even tested it on large motion and out-of-distribution scenarios.
And the performance gap just got wider. For large motion, Wan-Move's EPE was 3.0. The next best was way up at 4.1. It just shows how robust and generalizable the model is.
Of course, the ultimate test is always human evaluation.
Right. And in head-to-head comparisons, it had a win rate over 96% against models like Tora and Levitor.
But the real industry headline is the comparison to Kling 1.5 Pro.
That's the one. It showed competitive, sometimes even superior, win rates in motion quality. An open research method achieving parity with the top-tier closed commercial product. That's a huge statement.
Okay, so let's talk about what this unlocks. Because they chose point trajectories as the input, it enables a whole range of cool applications.
For sure. One of my favorites is motion transfer.
Yeah, that's really cool.
You can take a video of, say, a gear turning, extract its point trajectories, and then apply that exact motion to a totally different image, like a photo of a robot arm.
So you transfer the motion itself, not the appearance.
Exactly. And the camera control is also incredibly powerful.
This isn't just like a fake digital pan.
No, it's way more sophisticated. They use a depth predictor to figure out the 3D scene. Then they define a virtual camera path, a dolly in, a linear slide, and project that back into 2D trajectories for the model to follow.
Which is why the results feel like real camera moves, not just a warped image.
And they use a similar trick for 3D object rotation. Estimate depth, apply a 3D rotation, and then feed the resulting 2D trajectories into the model. It's all handled by the same LFR mechanism.
It's incredibly versatile. But to be impartial, we have to talk about the limitations.
Of course. No model is perfect. And the main constraints are tied directly to the input, to the point tracks.
Right. So if an object gets occluded for too long...
If it moves behind something else, the conditional signal is lost, and the control degrades. The object might just stop following its path.
They also noted that in really crowded scenes with tons of interacting objects, you can start to see some visual artifacts.
Yeah, the model can struggle to maintain coherence when there's just too much going on in the latent space.
And finally, the same problem all generative models still have.
Physical implausibility.
Right. The motion can be perfectly controlled according to the trajectory, but it might still violate the laws of physics.
And if the tracker that generates the trajectories makes a mistake, the model will faithfully follow that mistake. Garbage in, garbage out.
So if we pull it all together, the core achievement here is proving that efficient, high-quality motion control doesn't require bloating your architecture.
It just requires being smarter about how you use the architecture you already have. And latent feature replication is a brilliant way to do that.
And they backed it up. Performance parity with commercial tools and a massive 75x reduction in inference overhead compared to a ControlNet.
It really sets a new bar for efficiency. But for me, the most interesting part looking forward is the generalization.
You mean how it was trained on 200-point tracks but performs best with over 1,000 at inference?
Exactly. It can somehow interpolate and handle a density of control signals far beyond what it ever saw in training.
That's fascinating.
It really is. And it makes you wonder, what's next? If LFR is this good at explicit, detailed control, could we start to merge it with implicit control?
You mean generating motion that's never been annotated?
What if you could synthesize novel latent trajectories just from the text prompt alone? What is the next frontier of conditioning if it's not just feeding the model pixel space trajectories anymore?